All right, good morning. Or good night, depending on when you're watching this. Last night you guys watched a video introducing simplifying radicals. And it was an ed puzzle, and it went over numbers 1, 3, and 5 in your packet. So what I'd like you to do right now is I'd like you to try out numbers 2, 4, and 6 on your own. So you're going to pause the video and try them out. And then when you're done, hit play and see how you did. All right, so number 2. So if you look inside the radical, right, inside the square root, 28 is not a perfect square, and either is a to the 17th. So what we're going to do is we're going to set up underneath it or next to it, however you want to do it, we're going to set up 2 separate radicals. Okay, the first one is going to be where we put all of our perfect squares, and the second one's going to be where we put all the leftover material, right? So let's take a look first at just the number 28. We want to say, well, what's the biggest perfect square that divides evenly into 28? Well, the biggest perfect square is 4. And since 4 times 7 gives us 28, 7 is going to go in our leftover radical. Okay, and as long as you find the biggest perfect square that divides evenly into a number, whatever's in this leftover radical shouldn't simplify anymore. Okay, now let's look at our variable, a to the 17th. Now this is an odd exponent. Remember, if it's a perfect square, a variable needs to contain an even exponent. So let's think about it. What's the biggest perfect square that we can take out of a to the 17th? Well, what you should be saying to yourself is, what's the biggest even number that's less than 17? So 16 is. So in our perfect square radical, we're going to put a to the 16th power, right? That's the biggest perfect square that we can pull out of a to the 17th. So that leaves us with 1a, a to the first, that we're going to put in our leftover radical. All right, and then here, all we're going to do is simplify your perfect square radical and then bring down the leftover radical. So the square root of 4 is 2. And be careful, the square root of a to the 16th is not a to the 4th. Remember, when you take the square root of a term with of a variable with an exponent, you cut the exponent in half, okay? You divide it by 2. So the square root of a to the 16th would be a to the 8th, because a to the 8th times a to the 8th gives you a to the 16th, right? When you multiply two terms with the same base, we add these exponents. All right, and then just bring down the leftover radical. So radical 7a, and that would be the answer to number 2. All right, so number 4. Now, if you look within the radical, not everything is a perfect square. So, we're going to have to, again, set up 2 radicals. The first one's going to go where all our perfect squares go, and the second radical is going to be all the leftovers. All right, so let's start with this. Start with the number 50. 50 is not a perfect square, but the biggest perfect square that divides evenly into 50 is 25. So I'm going to put that here. And since 25 times 2 gives us 50, 2 is going to be what we left out, the leftovers. All right, now let's go to the first variable, which is an a to the 4th. Now look at this. This exponent is even. So if this is even, it means this term is a perfect square. So the whole entire term is going to make my perfect square radical. So I'm going to put a to the 4th in that first radical. Okay, and that means there's nothing left over for our non-perfect square radical. All right, now let's look at b to the 11th. Now 11 is an odd number. Remember, we need an even exponent in order for it to be a perfect square. So here, the biggest perfect square that I can pull out of b to the 11th is b to the 10th, right? Basically, you're saying to yourself, what is the biggest even number that's less than 11? Well, 10. So I'm going to put b to the 10th in my perfect square radical. And that just leaves me with 1b, or b to the first, in my leftover radical. All right, so now let's simplify. The square root of 25 is 5. The square root of a to the 4th is a squared. Okay, and if you notice, this is all coming out of the radical. We're taking the square root of each term. And the square root of b to the 10th is b to the 5th. Remember, you just take the exponent and you divide it by 2, right? You cut it in half. And then you can bring down your leftover radical, and this is the answer to number 4. Okay, this is what that radical simplifies to. All right, so now let's take a look at number 6. Now, this 2/3 in front, I'm just going to bring it down. I'm going to kind of move it to the left a little to give myself a little room, because the screen is not that big. And then it looks like we have some things within this radical that are not perfect squares. So I'm going to set up 2 separate radicals. My perfect square radical is the first one, and my leftover radical is the second one. All right, now 72 is not a perfect square. Now there's lots of perfect squares that divide evenly into 72, right? 1 divides evenly into it, 4 does, 9 does. I mean, there's lots of things that work, but you want to find the biggest perfect square that divides evenly into 72. I feel like the easiest way to do that is just take 72 and start dividing it by the smallest number possible. 72 divided by 2. If that doesn't give you a perfect square, go to 72 divided by 3. Because if you divide by the smallest number possible, wouldn't the answer be the biggest number that divides evenly into it? So you're looking for the biggest number. That's a perfect square. Anyway, when you do 72 divided by 2, it gives you 36. So 36 is the biggest perfect square that divides evenly into 72. And since 36 times 2 gives us 72, 2 is going to go in our leftover radical. All right, now let's look at the a to the 9th. Now don't be tricked, 9 is a perfect square, but because it's an exponent, a to the 9th isn't. Remember, you need an even exponent in order for it to be a perfect square. So the biggest even number that's less than 9 is 8, right? So a to the 8th is the biggest perfect square that we can take out of that term. So I'm going to put that here, and that leaves me with a to the 1st in my leftover radical. Okay, now let's go to the b. This says b to the 16th, and this term is a perfect square. Not because 16 is a perfect square, but because 16 is an even number. Okay, if our exponent is even, then the term is a perfect square. So I'm going to put that whole entire b to the 16th in my perfect square radical. All right, so now let me bring the 2/3 down. And we're going to simplify this radical. Now keep in mind, this is when you have 2/3 radical, there's really multiplication in between here. It's 2/3 times radical 36, a to the 8th, b to the 16th. So I'm going to be multiplying 2/3 by whatever this simplifies to. So you know what? Let's open up a parenthesis, right? That always implies multiplication. All right, so the square root of 36 is 6. The square root of a to the 8th, just cut the exponent in half, is a to the 4th. And the square root of b to the 16th is b to the 8th. And I'm going to bring down that radical 2a. Now the only other thing I want to do is I want to multiply 2/3 times what I have in here. Now isn't 6 the same thing as 6 over 1? Okay, so if we want to multiply these, I mean, you could do it a couple different ways. I'm just going to multiply the numerators and then multiply the denominators and divide. All right, so 6 times 2 is 12, right? And 3 times 1 is 3. So 12 divided by 3 is 4. So I'm left with 4, a to the 4th, b to the 8th, and then I'm going to bring down my radical 2a, and that's it. All right, you guys can flip to the back of this page now. Okay, so if you turn to the back of the page, just turn to page 2, here we're going to talk about perfect cubes and then perfect fourths as well. All right, so a perfect cube is just really the cube of a whole number. So if you take 1 and cube it, 1 cubed, 1 times 1 times 1 is 1. So I'm going to put that first on our list here. 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3 is 27, and so on. So I'm just going to list a few of these out. So 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and the list will just keep going. So I'm just going to write ... All right, now let's talk about variables. If we take an x and cube it, we would write that as x cubed. Okay, now if we took, let's say, an x squared and cubed it, well, when we have a power being raised to another power, we could just multiply these. So this will be x to the 6th power. All right, so now let's take x cubed and cube it. So when you have a power to power, you just multiply these, so that'll give you x to the 9th. If we take x to the 4th and cube it, that'll give us x to the 12th. So x to the 5th cube would be x to the 15th, and so on. Our list keeps going, so I'm just going to put ... Okay, so what you should notice about all of these exponents is they're all multiples of 3. Or another way of saying that is they're divisible by 3. So I'm going to write that out. So I'm just going to say the exponent is divisible by 3. Okay, just like a perfect square, the exponent is divisible by 2. Okay, so what we're going to do is if you take a look at number 7, we're going to simplify that. We're going to do it really the same way we simplify perfect squares. All right, so first thing you want to do is you want to look at what's under the radical. And if everything under here is not a perfect cube, we want to take this and separate it into 2 separate radicals, where the first radical is going to contain all of our perfect cubes, and the second radical is going to contain all the leftover terms. All right, so if we take 24, let's look at that and say, well, is that a perfect cube? If we look on our list up here, 24 is not on our list. So we want to say, well, what's the biggest perfect cube that divides evenly into 24? Well, 8 is. So I'm going to put 8 in our perfect cube radical. And then since 8 times 3 gives us 24, I'm going to put that leftover 3 right here. All right, so now let's look at our 8 to the 6th. If we look at the exponent, 6, that is a multiple of 3. That is divisible by 3. So 8 to the 6th is a perfect cube. So I'm going to take that and put the whole entire thing in our perfect cube radical. All right, now if we look at the b to the 10th, 10 is not divisible by 3, so b to the 10th is not a perfect cube. So we want to look at this and say, well, what's the biggest perfect cube, or what's the biggest multiple of 3, that we can pull out of a b to the 10th? So that's the biggest, multiple of 3 that's less than 10 would be 9, so we can pull out a b to the 9th. b to the 9th is a perfect cube, and that's going to leave us with just one b left over to put here. All right, so now let's just simplify our first radical. So the cube root of 8 would just be 2, because 2 times 2 times 2 gives you 8. The cube root of 8 to the 6th would be a to the 2nd, because a to the 2nd times itself gives you a to the 6th. A shortcut way, there's a rule, we say power divided by root. If you take your power and divide it by the root, that'll give you our exponent right here. So if we do this again, if we have b to the 9th, if we want to take the cube root of b to the 9th, we can write b, and then we'll do power divided by root. So 9 divided by 3 is 3, so that'll give us b cubed. And then you're just going to bring down the leftover radical. So this would be the answer for number 7. All right, so let's talk about perfect fourths, and it's really just going to follow kind of the same trend of everything we've been doing with perfect squares and perfect cubes. All right, so if we want to list out our numerical perfect fourths, let's see, 1 to the 4th, 1 times 1 times 1 times 1 is 1. 2 to the 4th, 2 times 2 times 2 times 2 is 16. 3 to the 4th is 81. 4 to the 4th is 256. And I guess I'll just do one more. 5 to the 4th power is 625. So it's a good idea to just kind of make a list of these first. All right, so now we knew that with variables, in order for it to be a perfect square, the exponent had to be a multiple of 2. In order for it to be a perfect cube, the exponent would have to be a multiple of 3. So in order for it to be a perfect fourth, the exponent would have to be a multiple of 4. So our first perfect fourth variable term would be x to the 4th. Okay, the next one, if you took x squared and raised it to the 4th power, it would give you x to the 8th. The next one, if you took x cubed and raised it to the 3rd power, it would give you x to the 12th. So you'll just see, you could see the trend. Our exponents here are just all the multiples of 4. And that list just keeps going and going, so we'll just put a dot, dot, dot. So if you just want to put a note here, just kind of like we did for the other ones, the exponents are divisible by 4. And we're not going to actually, do any more than this, but if you did perfect fifths, the exponents would be divisible by 5. Perfect sixths, the exponents would be divisible by 6, and so on. All right, so let's take a look at number 9 together. Now, if you look at the number right here, 162, that is not on our list. So what we're going to do is we're going to take our radical, and we're going to break it up into 2 separate radicals. All right, so you want to say, well, what's the biggest number that divides evenly into 162? That's on our list, so that's going to be 81. 81 times 2 gives us 162. So I'll put the 81 in the perfect fourth radical and the leftover 2 in the other radical. All right, so if we look at x to the 5th, well, 5 is not a multiple of 4. So what we're going to do is we're going to take out the biggest perfect fourth that we can. So the biggest perfect fourth that we could take out of this would be x to the fourth. And that would leave me with just an x in our leftover radical. All right, y to the 12th. This is a perfect fourth because 12 is a multiple of 4. So I'm going to take the whole thing and put it in our perfect fourth radical. All right, so then the fourth root of 81 is 3. And if you didn't know that, you could go in your calculator. If you hit math and scroll down until you see the xth root, so that would be choice 5, you could plug in, you could basically substitute that x with a 4, and you could plug in the fourth root of 81. All right, but anyway, the fourth root of 81 is 3. The fourth root of x to the fourth is just x to the first power, right? So we can write that as x. Again, 4 divided by 1 is 1. And then the fourth root of y to the 12th would be y cubed, because if you divide the exponents, right, take the power and divide it by the root, 12 divided by 4 is 3. And then you would just bring down your leftover radical. So what I'd like you guys to do right now, so if you are in lab or regular, you are going to try out number 8 and 10 on your own. And then you're just going to check with the answer key that's on Google Classroom. Okay, you're going to go down to Unit 4 Material, click on Answer Keys, and this handout is called Simplifying Radicals. If you are in honors, in addition to doing numbers 8 and 10 on this page, you're also going to do the extra practice on the next page, and then check your answers with the answer key as well. All right, see you guys tomorrow.